morning, everyone. I'll be doing my 6-minute talk on friction stir welding. So some brief historical background. Friction stir welding was invented by Wayne Thomas and the Welding Institute in 1991. If I remember correctly, it was first discovered actually by like a failed like machining thing, like they were trying to like mill something and accidentally welded two pieces together. So that's how they started to develop this technology. So its benefits are overcomes many problems associated with traditional joining technologies, and is also applicable for many different materials, but most commonly used for aluminum. So how does friction stir welding work? So friction stir welding is a solid state joining process, which this means is it applies just enough heat to soften the material without melting. So unlike fusion welding, there's no metal melted, it just uses friction to heat up the metal, soften it to where it plasticizes, and then mixes your two work pieces together. And so here I included some pictures of some fixed pin tool heads, just to give you an idea of what that might look like. So some advantages, there is no filler material required, or shielding glasses or any consumables at all. Usually you'll get minimum distortion, most of that coming from excess like friction from heat. Weld strength is usually identical, or at least your goal is to have a weld strength identical or better than the base material. It's cleaner, you don't have the off-gassing that you would have from traditional welding. And there's also 3 different types of tool heads depending on your, depending on your application. Here's what those look like. The tool heads I showed earlier were this fixed pin. Then you have adjustable pin, which this little white part here can like actuate in and out of your material depending on what you may need. And then of course there's the self-reacting, which self-reacting works with the same mechanism that moves this pin, it just moves another head up and down, and they spin in opposite directions. Here are some examples of friction stir weld machines. As you can see, they vary greatly in size. The one that I used in the class was this one right here, but there are obviously a lot larger ones for larger work pieces, such as rockets. So here are some disadvantages. It requires a lot of setup to perform these welds. These clamps are very time consuming to put on, and they have to be really tight because of how much force is required to perform these welds. Lots of preparation. You have to use these Scotch-Brite pads to sand off and smooth the weld surface. You also have to clean that with alcohol. And also the geometry of your weld surfaces can also be limited. So just some thermodynamic concepts to consider would be mostly conduction. There's a lot of heat generated from the stir pads, and most of what the weld engineers would try to do is like control your weld, because it obviously directly affects the quality of the weld. Not enough force. You can tell whether a weld is running too cold or hot by how the weld surface looks. So like if a weld is too cold and you don't have enough pressure on your surface, you'll still see like some of like the stir marks on it, but there will be like kind of little holes almost, or like it's like an uneven surface. And if your weld is running too hot, there's going to be excess flashing, so like a bunch of extra material kind of building up on the side because you're pushing too hard on Here's just a cool diagram to kind of show you the heat zones. It's like in the middle, you have your weld nugget, and right around that, you'll have your thermomechanically affected zone, and then your heat affected zone and your base material. This diagram for the weld nugget is different from fusion because this TMAS right here, the thermomechanical affected zone, is specific just for the stir welding and solid state manufacturing. A fusion zone only has like your weld nugget and then a heat affected zone and then your base material. Here, some general applications is mostly aerospace, where you can build frames, shells, tanks, and similar to like all those other industries. What's really cool is they do have stir deposition. I don't know if anyone in here is on the meld team, but that's what that is. And there has been some research done on stir welding, like metal added manufacturing parts together. It's like if you had like a powder bed part, I think there's research done on stir welding like a powder bed part to like a regular aluminum part. So here I just wanted to talk a little bit about the work that I did for the stir welding elective. So what we did in that class was we used a self-reacting weld, and we joined, like this was like a new weld joint that our instructor was exploring, where you have one plate here and a butt weld with two smaller plates. So you have a 3-plate joint, and the proposed application was like for fuel tanks such as this. And there's some extra information on that here. So here's pictures I took of like the test piece. See, here's what I kind of meant, like you can maybe be able to see like a little bit of flashing here. If your weld is too hot, that's whenever you get like really big like shards like jetting off to the side. But anyway, you can see we started the weld at the top here, and then you go all the way down these plates, and then here's where it tore out at the end. We started at the beginning of the weld. You can see that like there's a lot of oscillation and like vibration until it kind of smoothed out halfway down the weld. And I'll talk a little more about that later. Here was our force graph where you can really see all those oscillations. And we think that was more due to like improper clamping, or like something might not be clamped as much. It was also on this end, or that's where we started, but on this end, as we were watching our weld, you could see the two plates were kind of like splitting apart. So it was kind of a weld gap that formed. That's also what we think was due to clamping issues. But also here's a macro for like what the weld actually looked like. And you can see the two plates here are weld, and then the plate on the side. And this lip here was formed because that plate is slightly taller than these two plates together, so that's just the tool head kind of digging in to the bigger plate on the side. So that's just kind of my overview on friction stir welding, and here are my sources. So does anyone have a question?